And welcome to my presentation. So, like already introduced, I will talk about impedance-spectroscopy-supported microchannel flow rate sensors. So now we could ask, why would we want to know the flow rate in such a small microchannel? So sometimes we need to synchronize the flow rates, mass flow rates, volume flow rates of subsystems of such a microchannel. So the keyword here is lab on a chip. So we need, for example, to know the volume flow because we want to mix fluids, we want to do some chemical reactions, and for that we need to know the mass which goes into our reservoir, the mass which flows through our channel. So here's a small introduction. This is only a schematic of the microchannel with the impedance electrodes on the left and the right-hand side, the white ones. In this inset, you see badly a little bad picture of the real microchannel. My microchannel is molded from polydimethyl siloxane, short PDMS, and the liquid flows through the channel with a varying flow rate V. And what we see is that if we take an impedance spectrum in a certain frequency range, that the impedance spectrum changes dependent on the flow rate. And we want to model the equivalent circuit of this microchannel, and this change with different flow rates is visible in both the Bode plot. So Bode plot is amplitude plot, Nyquist plot, and phase plot, and also the fit with the equivalent circuit parameters. So everybody of you knows what the result of an impedance measurement is. So you have your amplitude plot, it's the impedance over the excitation frequency F, the phase plot phi over the excitation frequency F, and the Nyquist plot, which is the imaginary part of the impedance versus the real part. And my measurement workflow and setup is we have this KT scientific pump to get a constant volume flow. Then the flow goes into the PDMS microchannel, and I take an impedance spectrum with a Zurich Instruments MFIA impedance analyzer, which reaches from 100 Hertz to 5 megahertz. I excite this via a sinus signal and model the equivalent circuits then. So the measurement, the Bode plot and the phase plot on the right-hand side is only exemplary. This has nothing to do with our measurement. So the typical approach to model such an equivalent circuit is measurement of phase and amplitude alone does not yield a final result for the properties of the microchannel. So you need to know a little bit more. You need a relation between the data and the system. And this relation is given by the so-called electrical equivalent circuit, which describes the distinct elements of the channel. So you see here on the bottom, the equivalent channel, the equivalent circuit we used for our microchannel. For example, on the left hand and the right hand side, you see the wire inductances and the wire resistance. In the middle, this is the fluid capacity and the fluid resistivity. And the two parts on the left hand side where CDL and CPE is, this part is called Randall's circuit. So this describes mostly the interface between a metal electrode and an ionic fluid and the physical appearance, physical stuff, which happens there, but more on that later. So elements of an equivalent circuits are rather boring. So we have an ohmic resistance R, whose phase shift is 0 degree. Then we have, of course, inductance, where the phase shift goes to plus 90 degree, and the capacitance, where the phase shift goes to minus 90 degrees. So this would be in a normal electrical network. But if we have to deal with fluids and interfaces between metals and fluids, there are two other things. This is, for example, the constant phase element, CPE, and the Warburg element, W. The constant phase element is an element of the equivalent circuit which mainly affects the ionic double layer on the electrode. So you can see how the impedance of the constant phase element is defined. It's defined by 1 divided by the admittance, of course, and this is defined by 1 divided by Q omega to the power of alpha. And this Q and alpha tuning parameters, where you can decide if the constant element phase is more like a resistor or more like a capacitance. So depends what phase your system is in on a given frequency. On the other hand, the Warburg element, the impedance of the Warburg element ZW is given here. So it's noticeable that the real and the imaginary part is always the same. And I will spare you the details of this Warburg parameter AW. This RT divided by all these variables. You have diffusion constant in there, temperature, Faraday constant, and so on. And this describes mainly diffusion effects inside your fluid, inside your system, which you want to describe with your equivalent circuit. So because of symmetry, the equivalent circuit, because we want to fit it later so it gets more easy, we can reduce it. Of course, the inductances and the resistivity of the wire is in series, so we can combine this. On the right-hand side, you see only one of that with the relations between the full and the reduced equivalent circuit. For example, RK1 is the same as RK2, of course, because we say it's symmetric and same. And this is 0.5 times RTK. So the fluid capacity and fluid resistivity doesn't change by converting the equivalent circuit, but the Randall circuit changes, and also the relations of the parameters between the full and reduced equivalent circuit for the Randall circuit is shown here. So then I show you the first measurements for volume flow and conductivity. On the left-hand side, you have conductivity, amplitude, phase, and Nyquist. On the right-hand side, you have volume flow. For the conductivity, I used the static fluid and I measured between 350 and 1,300 microsiemens per centimeter. And for the volume flow measurements, I used tap water and measured from volume velocity or the volume mass flow from 3 to 15 milliliter per minute. And what you see first is that the measurement of the conductivity somehow sets the baseline for the volume flow measurement. The higher the conductivity is, the less you see, the less you can distinct in the volume flow measurements. For example, we can say now that knowledge is needed for both variables. And what you see here, for example, on the right-hand side. So you see only a very small difference between the different volume flows in the amplitude plot and in the Nyquist plot. And now the question is this a channel effect or is this an ionic effect? So there are a lot of works who state this is only a geometric effect. Because, for example, if you have a very fast volume flow or a very low volume flow, maybe if you have a soft channel like PDMS, the channel widens or the channel narrows, then the capacity of the fluid, of the electrodes and the fluid in between changes, and also the line resistivity of the fluid changes. But this is also measurable in hard channels like PMMA. So of course, there is a geometric effect inside, but there is also an ionic effect, and I did the equivalent circuit fitting to show that there is an ionic effect. So this again are the results for volume flow and conductivity using a third dimension. These are the same measurements, only with the frequency as third dimension. So the conductivity here shows the reduction of the total impedance relative to the 350 microsiemens per centimeter curve. So that's why on the y-axis we have impedance drop here. It's highly nonlinear, and like I mentioned before, it sets the baseline somehow for the volume flow measurements. And for the volume flow, it shows the reduction of the total impedance relative to the 3 milliliter per minute curve. And we see here that the highest discriminability between different volume flows is at low frequencies at about 100 Hertz. So for a given conductivity, we can measure the flow rate by impedance spectroscopy. For the sake of completeness, you always should take a look at your errors you make during measurement. So I show you the measurement error band for amplitude, phase, and the Nyquist plot using the example of a volume flow measurement at 3 milliliter per minute. Every impedance analyzer has parameters A1, A2, B1, B2, maybe C, and so on. Beta are also a nice number which they are using. These are frequency dependent. And with the two formulas on the bottom, you can calculate for each measurement point the percentage deviation and the deviation in degree for both the impedance and the phase. And for example, on the right-hand side, you see the phase at the frequency of 10 to the power of 7. The error band gets very wide because one of the parameters is frequency dependent. It gets big in this frequency region. So after the measurements, we have to do a fit. This is also only exemplary for this equivalent circuit on the right-hand side. This is not ours. And first, I did fitting of amplitude, phase, and Nyquist data by hand using MATLAB. And the values are strongly nonlinear dependent from each other. And there are several possible ways how to fit a certain equivalent circuit. So in our case, there are at least two possibilities how to fit the impedance equation. And that's a problem because there is a fundamental knowledge of the occurring physical processes and the orders of magnitudes, for example, the capacity of the fluid or the resistivity of the fluid needed. So there is no random short fitting possible. So you say, hey, I fit this and this is okay. This is my result that does not work. So for our equivalent circuit, on the right hand side, this is the reduced equivalent circuit. The solution converges to two options, how to model this equivalent circuit. These are the red and the black lines here. I wrote blue lines. So one option, you have in this table the parameters from RF down to alpha and the parameters option 1 and option 2, which both succeed the fitting. So as a spoiler, the option 1 is the correct one. The blue one is the overall curve, which is the overall curve between the black curves. And why do I know that option 1 is the real one? Because the correct value for the capacity of the fluid can be estimated by utilizing the known channel geometry, for example, channel dimension, and RF can be estimated by simple conductivity measurements at a fixed frequency. So we know that option 1 is correct. And now I did this for every volume flow and every conductivity. And what we get now, so you have a table here on the right-hand side for all fitting parameters of the equivalent circuit for different volume flows, for different conductivities. And if you look at the left-hand side on the first picture here, the water capacity. The water capacity does not change. So this is not a geometric effect due to a changing, widening, or a broadening microchannel. What does change and very strongly is the CPE parameter Q and alpha. And this is a very strong hint that this is an ionic effect. So the volume flow changes the equivalent circuit parameters. It does not change the bulk capacity. And our double layer properties, where we are working with, are composed in the left-hand side, the Rendell circuit in CDL, CPE, and the transfer resistance RTF. So what I wanted to show here is that this is measurable and it's not a geometric effect alone. And with these words, I will end my presentation. And if you have any questions, please ask.